Hello, everyone, and welcome to today's Crunch seminar. I'm Nazanin. I'm delighted to be your host today. Today, we have two speakers to talk. Our first speaker is Amin Pashaei Kalajahi. He will be giving a talk on input parameterized physics-informed neural networks for denoising super-resolution and imaging artifact mitigation in time-resolved three-dimensional phase contrast magnetic resonance imaging. Amin Pashaei is a PhD candidate in mechanical engineering at the University of Wisconsin-Milwaukee, working under supervision of Dr. Roshan D'Souza. He developed the Input Parameterized Physics-Informed Neural Network (IP-PIN) framework, which integrates fluid dynamics and MRI physics to enhance 4D flow MRI data. His method significantly reduces processing time and improves diagnostic quality by mitigating noise, velocity aliasing, and phase offset errors. His research interests include scientific machine learning, cardiovascular fluid mechanics, and medical imaging. With that short introduction, the floor is yours, and you can start your presentation.
Sure, thank you. Well, hello, everyone. Thank you for the introduction, and also thank you for inviting me to talk about our research. So today, what we're looking at is super resolution denoising and artifact correction for the time-resolved 3D PC MRI, or basically 4D flow MRI, using physics-informed neural network. But the way we are looking at it is a bit different approach compared to conventional pens. Basically, our approach is to parameterize the pin solutions with respect to input data to reduce the processing time if we have any new and unseen data sets by the framework. This research has been funded by two grants from NSF with the numbers I mentioned in this slide. With that, I will continue. So here's the agenda for my presentation today. I'll start with the motivation for conducting this research. Then I'll have a brief explanation of 4D flow MRI and its limitations. Then I'll introduce our proposed input parameterized pin, and it will follow by results, conclusion, and potential future work. So basically, studying hemodynamics is essential for understanding where and how cardiovascular disease develop, because fluid forces directly influence vascular cell behavior through mechanical transduction. And basically, abnormal flow patterns translate to abnormal biology. They provoke endothelial dysfunction, drive inflammation, and ultimately shape where disease like aneurysms occur. So focusing on hemodynamics behavior and flow-derived forces provide deep insight into disease mechanisms and guides better actually predictions, diagnosis, and basically intervention for cardiovascular disease. This is a brief introduction to 4D flow MRI, and basically 4D flow MRI is a non-invasive phase contrast imaging technique for capturing volumetric time-resolved flow maps in human blood vessels or vascular structures. It offers significant advantages, but also comes with limitations such as spatiotemporally average data due to finite spatial resolution and the time taken to scan velocities in the cardiac cycle. And flow MRI acquisition processes basically is as shown in this figure. Considering pulsatile nature of the cardiovascular flow, the cardiac cycle basically is divided into a number of so-called cardiac phases. And due to the time it takes to complete the volumetric scans and fill the K-space for the particular cardiac phase, the acquisition process is spread over several cardiac cycles. And for each of these cardiac phases, this finite times, typically for the conventional 4D flow MRI, a minimum of 4 scans are required, including 3 directional velocity encoded scans and 1 velocity compensated reference scan. And for the velocity encoded scans, the bipolar gradients coil are being used, which consists of a sequence of 2 gradient pulses with the same magnitude, but one negative and other positive. And this configuration results in having phase shifts in moving spins and basically 0 phase shifts in the static tissues. And the velocity-induced phase shifts are basically isolated by subtracting the reference scan from the velocity encoded scans. And basically, this is the physics or math behind the acquisition. The MRI's velocity encoded signal in each direction is the sum of the apparent spin densities or the proton densities and the acquisition noise, which by using inverse Fourier transform, we can have it in the complex image space. And the apparent spin density is combination of magnitude image and phase images, basically, where phase image include the phase offset errors or so-called non-velocity phase due to various sources. And the other part of this phase is basically the tissue velocity induced phase, which encodes the velocity of the tissue between pi and negative pi based on some user-defined parameter called velocity encoding parameter or rank. And basically this rank is the maximum anticipated velocity. And it will generate some issues that I will explain in coming slides if we have like anticipated less maximum velocity that we will have an underlying flow. Basically, the MRI images are discrete, and the value of the apparent spin density at voxel is basically spatiotemporally average of the apparent spin density convolved with acquisition point spread function of the MRI. So finally, the discrete Cartesian images of the 4D flow MRI will be like this equation. This is the summation of the apparent spin density and the noise. About the application of 4D flow MRI, so data acquired by 4D flow MRI is used for assessing hemodynamics parameters such as flow rates and basically wall shear stress, which is a very important parameter. And basically, wall shear stress is the force that blood exerts on the vessel walls. And for calculating the accurate wall shear stress, we need velocity gradients, and also we need the accurate vessel boundaries. And because of the limitations of 4D flow, segmenting the accurate vessel boundaries using like pure 4D flow MRI data has some problems. And about the limitations of 4D flow suffers from several limitations, including low spatial and temporal resolutions. If you're looking at the major blood vessels like aorta, it may not be a problem. But when you're looking at the small blood vessels, like in brain, this resolution may not be sufficient for all sorts of analysis. Other issue, we have acquisition noise, velocity aliasing, and phase offsets errors due to eddy current induced by the bipolar gradient encodings. And the last one is basically prolonged acquisition times, which usually takes about 15 to 20 minutes. And so this is the typical cerebrovascular structure. And the spatial resolution of 4D flow MRI is typically between 0.7 millimeter and 1 millimeter, which is insufficient for small vessels like cerebrovascular structures. So it is inefficient to get velocity gradients in this sort of resolution. And also you cannot segment the geometry cleanly. And this results in very inaccurate wall shear stress calculations. The other issue is noise acquisition. Ye-
I have a question
yes,
about the temporal resolution. You said the temporal resolution is 80 milliseconds, which
correct,
seems to me it's pretty good, right? Because it's 1 second, the cardiac cycle. So
correct.
80
But when
milliseconds is very good.
usually, yeah, 80
You have
milliseconds
100
for
points per cycle.
yeah, but yeah, for like some aneurysm treatment and diagnosis, it may have some problems using this temporal resolution. But still, we are able to improve this temporal resolution as well. So if we can improve it, why not?
Sure.
Yeah, about acquisition noise. Acquisition noise is a common issue in 4D flow MRI that affect both magnitude and flow encoded images. Basically, the acquisition happens in frequency space, and noise is zero mean Gaussian noise. And by converting data into image space using inverse Fourier transform, which is basically a linear transform, noise will have the same characteristic, zero mean Gaussian. However, when we are calculating the magnitude and phase images from the complex images, the calculation will be nonlinear operations. So basically, the noise will change the characteristics, and we don't have Gaussian zero mean noise anymore. Other issue that for the flow MRI has is velocity aliasing. Velocity aliasing basically is where the actual velocity exceeds the encoding parameter or range parameter that causes the measured phase to wrap around the maximum measurable velocity. This leads in like fake sharp negative or sharp positive velocities, as you can see in this image on the left-hand side. And the phase errors are, the background phase errors are resultant of various sources, including chemical shifts, magnetic susceptibility, hardware inconsistencies, and basically electromagnetic eddy currents. And it impacts the flow measurements. And conventionally, these errors are corrected by scanning the static region and applying a function fit and subtracting from the flow region, which is problematic if we don't have enough static regions. So to address these limitations, basically one of the solutions are CFD simulations or patient-specific CFD simulations. And the patient-specific CFD simulations are basically used to overcome these limitations for different imaging techniques, such as like low spatial temporal resolution and any other artifacts. And these simulations provide high-resolution simulations of the blood flow within the anatomical models by solving Navier-Stokes equation under particular assumptions of the flow models. Typically, for doing these simulations, vascular geometry is derived from segmented scans using angiograph techniques like CT angio or contrast-enhanced MR angios. And it will follow by meshing into finite elements or finite volumes and applying boundary conditions, which are often derived from 2D PCMR for the flow MRI or Doppler imaging. So these CFD simulations reliability are often limited by several key issues like assumptions made in flow models, errors in boundary condition estimation, geometry errors introduced by inaccurate segmentation of the vascular structure, and basically errors in model parameters. So CFD simulations produce physically feasible flow fields. These flow obey the Navier-Stokes equations, visually compelling representation of flow dynamics, but fidelity of these results remain questionable. People have used other approaches to enhance the accuracy and reliability of numerical simulations by integrating experimental and observational data into computational model. The objective is to reduce the uncertainty inherent in CFD models by updating models with real-world data. And however, these methods also have limitations. They often require computationally extensive CFD simulations or an extensive library of possible flow fields. Also, there are other challenges like accurate registration between CFD domains and imaging domain. So the problem with this approach is you still need the CFD models. You need geometry, so on and so forth, which is very tedious and time consuming. Our goal is not to do any of these. So to address all of these limitations, the limitation of 4D flow MRI and other approaches, we propose deep learning based framework that we call input parameterized physics informed neural networks, or basically IPPN, for super resolving 4D flow MRIs while addressing acquisition noise, artifacts due to velocity aliasing, and background phase offset errors. Basically, this figure shows the operation of our proposed IPPN framework. Essentially, you can think of it as a physics-informed magnifying glass. User selects a special temporal region of interest from the flow region, which may include vessel boundaries as well. And here we are operating on complex image space data, not the velocity maps. And this selection of ROI includes the real and imaginary part of only 3 velocity encoded scans. We don't need the reference scan here. All of the data are in complex images space. And basically, framework processes this data considering the flow physics and MR acquisition mechanics and generates super resolved artifact and noise-free velocity maps. On top of that, we will generate magnitude images. And notably, unlike typical for the flow MRI, like 4-point acquisition, which requires reference scan on top of these velocity encoded scans. Our framework operate only on velocity encoded scans. And this way we cut down the amount of data that we need by 25%. And our proposed IPPN network is a fully constrained neural network, which combined with the convolutional encoder for parameterizing the network with respect to the input complex velocity encoded scans. And this approach enables generalizability, and which avoids the costly task of ab initio training for new data sets. And basically, this is the structure of our proposed framework. It has two different parts. First, a flow image encoder that takes the complex data from region of interest, the user selected region, in 3 flow encoded scans as the input, and generates a latent vector, or basically a features vector. And this encoder includes a couple of, to be precise, 4 3D resident blocks and one 1D convolutional layer at the end of the network. And the generated latent vector, along with the local spatiotemporal coordinates, are fed into 2 separate physics-informed MLPs, which one of them generates normalized velocities, relative pressure, and the magnitude image, and the other one basically predicts 3 directional so-called non-velocity phases. And we also have here, we use neuron-wise adaptive silo activation function. Basically, this structure allows for parameterizing with respect to the input image data, and also retain the benefits of conventional pins like generating continuous output functions. Like other pin approaches, we employ the compound loss function, incorporating a data fidelity term and physics regularization term, which are weighted by parameter alpha that adjust the relative importance of the data loss term and the physics regularization term.
I mean, I have a question.
Yes, Professor. Yes.
And can you please go back one slide?
Yes.
Okay, so I can understand the image in the top one. So you have the the next one.
Yes. Sorry.
But the when you have this 2 perceptrons, m theta 1 and m theta 2 and m theta 3.
Yes.
Why you have 2 different ones? Looks like
Actually, I tried to combine the outputs in a single MLP. We didn't succeed with that. So separating the outputs for non-velocity phases helped us a lot. So we were able to, by separating these networks, we were able to generate more accurate results.
But can you say what is, because the input for the theta 3 seems to be only the coordinates.
No. All of these latent vector as well as the coordinates are being fed into both of these MLPs. The input will be the same for both.
So why you need 2? Is it because you can make a much bigger perceptron, right? I mean,
Right, but
the
that's
two
really
m theta 2 and m theta 3 are identical, or
the
not?
size of the networks are different. The size that we use for number of layers and number of neurons for these 2 networks are different. But yeah, first we tried to have a single neural network with like multiple outputs for all of these. We were not able to get like very accurate results using that, so we decided to try this architecture, which was successful. But yeah, we can try. That's possible. We can try different architectures, like bigger networks. It depends on the computational power that we have.
Can you tell us what is phi b phi b x phi b y? Are these volume averages? What are these in
Sorry.
the lower phi b
Yes,
phi
these are
b
the,
phi sub b
correct. These are basically, as I
in the
mentioned
bottom one? In the bottom one.
yes, this one, you mean? I don't know if you can see my cursor, but you mean M theta trees outputs. Basically, these are outputs that
Right.
are non-velocity phase that introduced by the MR machine itself to the images, acquired images. So let me go back to equations. The signal that comes from MR machine has two parts for the last equation here. So it has two parts basically for the phase data. It has one part for basically the velocity encoded part of the that's actually velocity of the tissue that we're imaging. But there are other non-velocity phases
I
in
see. I
these
see.
images.
I see it.
Yeah,
The magnitude and the phase in the complex. I see it. Yeah,
correct, correct.
I get
So
it.
we're actually using our framework. We are able to predict that that non-velocity phase as well. So we need to subtract them from the data to get the actual underlying velocities.
Okay.
Yeah,
Thank you.
sure.
Hi, I'm Nikhil. I'm a PhD student in the graduate. I have a small question. If you go to slide
Sure.
16,
16. Yes.
yeah, can you tell me more about what you mean by selecting a region of interest? So what is that input? So that you are showing a geometry, right? So the geometry is segmented or what exactly it is? Like what goes with the input?
Correct. So the geometry here, basically, I want to show some symbolic representation of the imaging domain. So I mean by regional interest that we are interested in super resolving the data is not the whole domain of imaging domain. We're just operating on some part of it, some crop of this domain. So it seems like you're putting a magnifying glass on the domain. So if you check these shopping websites, if you put
Right.
your cursor on, it operates the same way actually.
Okay.
Yeah.
Mm.
Right. Thank you.
Sorry, I
Sure.
also have a question on
Yes.
slide 17.
Yeah.
Yeah. So here I feel like I don't know if you're familiar with DeepONet.
Yes. Yes. That's a very good question actually.
Can
Yeah.
we just use like a DeepONet here, like input your images to the branch and then your coordinates to the trunk, and then using that constructing the PDE and then.
Actually, that's a very good question. We're considering that approach as well, but at this stage of research, we wanted to keep it as simple as possible. We're not using any fancy neural networks here, just simple convolutional neural networks, simple MLPs. We were able to get very good results using that, but still, if we want to improve the architecture, yeah, the DeepONet is the first option that comes in mind. Yeah, we will try that as well.
Okay, thanks.
Sure. So yeah, about the fidelity loss function that's used. The data fidelity term basically minimizes the difference between predicted quantities and the target quantities. Here we implemented the data fidelity in complex image space, not velocity data or not magnitude data. This way, by operating in complex image space, we can handle noise easier because in this space we know the characteristics of the noise. If we want, we can apply filters to get rid of noise. Also, by implementing the data fidelity in this space, we avoid the velocity aliasing problem by nature. We are not operating basically velocity aliasing in image space as almost non-existence. When we get the velocity maps, we will encounter this issue, and we are avoiding this issue by nature by operating in this image space. So applying the data fidelity term starts with computing the dimensional predicted velocities and then calculating basically the predicted velocity induced phases considering the weight parameter. And from here, using predicted magnitude and predicted phase offsets, we calculated the predicted apparent spin density. And then basically, since we're operating in image space, the spatial temperature averaging is applied here on the voxel basis. And we approximate the discrete spin density at any locations that we're interested. So finally, the fidelity function basically minimizes the difference with the input flow encoded data. And the physics loss equation basically includes non-dimensional momentum balance equations and mass balance equations, which we are imposing these equations at an arbitrary number of points within the region of interest. So for testing our algorithm and basically pre-training and testing on unseen data sets, we generated two different patient-specific and steady CFD data sets for posterior cerebral artery aneurysm, another one for medial cerebral artery aneurysm. We use synthetic flow image scan data derived from PCA simulation for pre-training neural network and use the MCA aneurysm datasets for testing the performance of our framework on unseen new datasets. This is how we generated the synthetic datasets. Basically, we implemented patient-specific high-resolution CFD datasets. The flow encoded scan data were generated using velocity phase and calculate from the velocity images. Magnitude images that we are using here, synthetically, we put 1 for inside, 0.1 for outside. And this follows by averaging on per voxel basis and adding noise in the frequency space. And we have used different order of polynomials for this non-velocity phases. We use linear for pre-training, quadratic for test data. So these are the error metrics that we use. We employ the comprehensive set of error metrics, including root mean square, coefficient of determination, median absolute error, and relative percent error. And basically, this is the visual comparison of the predicted velocity fields to the ground truth. The left two columns correspond to the real and imaginary part of the flow encoded scans, which are basically the input to our framework. And these data contain phase offset error and acquisition frequency noise that correspond to signal to noise ratio of 20 decibel. The middle column here shows the velocity fields obtained from the phase of the complex images. This is what you see if you use the conventional methods. We are not using these velocities in any part of our training or in any part of our framework. And we can see that the algorithm successfully reconstructs the velocity fields at high resolution and captures all of the flow details. And this is basically the issue that I was talking at the beginning of the presentation. This is the velocity I'm using. If you check the middle row for the low resolution velocity for V component, this is when velocity aliasing happens. If we set a range parameter below the actual maximum velocities, the phase will wrap around the maximum velocity and you'll see such a sharp like artifacts in your velocity images, but we can see that our algorithm easily takes care of that. We don't have any aliasing issues in our predicted velocities. Also, these input data has a noise level corresponding to signal to noise ratio of 10 decibel, which is pretty high noise for MRI data. And this figure shows the results of temporal super resolution. Here we evaluated the neural network because basically it's a pin, so we have the continuous function for space and time. Here we evaluated the predictions at 4 times finer temporal resolution. So the temporal resolution for synthetic 4D flow MRI, it was 60 milliseconds, and here we are evaluating at 15 milliseconds. And we also compared the performance of the IP pin to conventional physics-informed neural networks, as well as the divergence-free radial basis function approximations. We can see the superiority of IP pin in capturing flow details and overcoming the noise in the input data compared to other two methods. So this is the list of the achieved error metrics employing our framework, also conventional pin, just the pure MLP pin, and divergence-free radial basis function. We can see the enhanced performance of the IP pin framework over other two. Here, by using generalizability of the IP pin, we use pre-trained network on PCA datasets and evaluated on MCA datasets for for the processing this MCA, just the regional interest of this MCA aneurysm, the training time or the processing time reduced like 20-fold. So for the pure MLP pin, it was like in half an hour. By our neural network, we were able to generate these results in like 90 seconds. And basically, this is the magnitude image prediction without using any reference data, just using velocity encoded scans. We are able to generate high resolution magnitude images. And we can use this, basically this magnitude image to segment the boundary of the region of interest or vessel boundaries. And this is the video of the segmentation using the magnitude image. We applied the marching cubes and we can see the pretty good accuracy and predictions compared to CFD. Sorry. In conclusion, we have basically successfully developed the input parameterized pin for processing actually 3-point acquisition for the flow MRI with super resolution and also correction for noise, velocity aliasing, and eddy current phase offset in a unified framework. We only use velocity encoded or flow encoded images. We didn't use reference scan here. We also are able to generate high resolution magnitude image which can be used for segmenting the boundaries. We did the training with image data, not ground truth, basically because for the flow MRI, you will never have the ground truth data. So we're not using any ground truth, but whenever we have access to that ground truth, we can incorporate them within our framework. So the method enables generalizability feature for MLP pins, conventional pins, and the method has successfully tested unsimulated for the flow MRI data. In the expanding our framework in the new phase of this work, we have expanded the application of the IPPN framework to process only 1 point for the flow MRI data and generate super resolved volumetric, basically 3D, 3C velocity fields for entire spatially temporal region of interest. As I mentioned earlier, conventionally for the flow MRI requires 4-point acquisition sequence, which is like 1 for reference scan, 3 other velocity encoded scans. But here we're proposing acquiring velocity encoded data using only bipolar gradient per scan, only 1 bipolar gradient per scan, and basically alternate and activate the different bipolar gradients across consecutive cardiac phases. And using only these velocity encoded scans, we are able to construct 3D, 3C velocities for the entire region of interest. And this way, we potentially reduce the scan time by 75%. And also in this new phase of the research, we extended the IPPN to directly process case-based data, not the image-based data. And by reformulating the data of delta in case space, we can enforce agreement with the raw case-based data. Also, in reality, with the MR machine, because you're doing finite case space and windowing, basically the windowing the case space, this case space window results in a sync point spread function with infinite supporting image space. And since we are operating only on region of interest, by implementing data fidelity in case space, we avoid the convolution with the sync function in image space. Also, operating on case-based data enables us to account for end effect of the other factors like T2 star and T2 and T2 star effects by incorporating them in the fidelity function. So as a potential future work, we're planning to validate our framework using the in vitro for the MRI data, also addressing phase error due to non-negligible acceleration pulsatile flows. And also we are planning to address the turbulent flows, application of moving boundary problems, and basically apply level set approaches to extract accurate boundaries. At the end of my presentation, I wanted to thank my supervisor, Dr. Roshan D'Souza, at our complex system simulation lab at UWM, and other team members here. Also, I want to thank our collaborators, Dr. Amr Hussein Arzani and Dr. Omid Amidu. And with that, I will conclude my presentation. Thank you for your attention. I will take some questions.
Thank you so much for your talk. Do we have any?
Course.
Yes, Vivek.
Hey, hi, my name is
Hi.
Vivek. I'm a PhD student working with Professor George Kaniadakis. Thank you for the great talk. I had a question regarding the simulations you performed to simulate the flow of the blood in the heart. So, were you considering like a fixed or rigid walls of the heart vessels, or were you considering it to be moving as the flow goes, which I assume is how it works, but I'm not sure. But yes.
Honestly, the CFD simulation parts that come from our collaborators, I'm not aware of all of the details, but here I believe we didn't use any moving boundaries. It's just rigid boundary. Yeah, but in the future part of our work, we are planning to apply moving boundary as well.
Understood. Thank you. I
Yeah.
assume that will be helpful when you apply on the actual MRI data. That's all.
Of
Thank you.
course, of course. Sure.
Thank you.
Yeah.
Nick.
Hi, I have one more question. So I was just wondering when you incorporate your in your loss function, did you incorporate any material properties of vessel, like the stiffness or something? Or
No,
not
nothing.
really?
Nothing. We didn't apply any other. Actually, we even didn't apply the non-sleep condition as well. We just used the pure data itself.
Because I was wondering when you did the training testing, right? When you do your pre-training, so if your vessel properties change, let's say for the testing scenario, I was just wondering how it will perform over there in that case.
Yeah, if we have access to exact location of the geometry, we can impose that. But usually, you don't have access using the data that you're acquiring for the full MRI. That's why we decide to keep as realistic as possible. But again, for new data sets, we still need that mini training for. So we are just starting from good approximation for initial condition, but we need that mini training on the new data. That's where this happens in
I see.
fidelity data to converge to new data. Yeah.
Thank you.
Yes.
Yeah.
Max has a question. Can you introduce yourself first and then, yeah.
Yes, of course. Hi, I'm Maximilian Dresper from Karlsruhe Institute of Technology. And first of all, thanks very much for the interesting talk. I have a question regarding how do you align your convolutional features or the domain where you extract them with the spatiotemporal input coordinates? Is it always the center, or how do you ensure that the convolutional features are aligned with the coordinates?
Basically, we are applying the convolution on entire regional interest, but we don't care which exact point are located in which coordinates. We're just creating a feature vector that will be repeated for all of the points. It will increase the size of the network, but this way we don't need to interpolate for all of the points that we are putting to MLPs. So basically, yeah, we're just generating a feature vector, but we don't care this feature as basically actually this feature vector is true for entire region, not for a specific coordinates.
Okay, I see. And then if you take only the small region of interest, do you slide it across the whole domain to reconstruct it? Okay.
Yes. Yes.
Okay, thank you very much.
Sure.
Okay. Do we have any other questions for the speaker from the audience?
Yeah, actually, I might have one. Oh, sorry, I was jumping the queue. I'm sorry, somebody else is first.
No, go ahead.
Oh,
But
okay.
first introduce yourself.
Sure. Hi, I'm Sasha Ranslu from Brown. I think the camera takes a few seconds to come up. So my question is, sir, you alluded to it towards segmentation. And I think this could be interesting in terms of because sorry, the camera doesn't seem to work actually. I'm sorry for that. What I find interesting is what you find a lot in segmentation is that it's very easy to segment in a way that disrespects those lip conditions where you have kind of a flow through the wall, which is unphysical. Have you been thinking about that segmentation that respects this no-slip condition on the boundary?
Right. Actually, we didn't impose a non-slip condition, but this segmentation using magnitude image is very rough estimation. That's why I mentioned we're gonna improve it in future work. We can apply other approaches like level sets to improve this. But we are using this magnitude image, which is embedded in input data, which is kind of embedded in like if you let me go back to this equations from MRI acquisition. So when we're dealing with velocity encoded images, the magnitude image is implicitly embedded in this data, in this velocity encoded images. So that's where we can apply this data fidelity and basically predict the magnitude image accurately. So that's alleviate using like non-slip condition, but still if we have like the good initial guess and we want to improve this prediction for boundary, we can use this magnitude image as initial guess for our boundary of the vessel and impose the non-slip condition there. That will improve our predictions, not only for segmentation, but also for velocities as well.
Okay, good. Thank you very much.
Yeah, of course.
Thank you. Do we have any other questions for the speaker? Any comments? I don't think so. Thank you so much for your great talk and for your
Thank you.
joining.
Thank you.
Thank you for joining us today. So I think it's time to move on to our second session and second speaker. Our second speaker is Chanwook Park. He will be giving a talk on interpolating neural networks and its derivatives for the next generation of predictive scientific artificial intelligence. Chanwook Park is a PhD candidate, recently completed his PhD defense in mechanical engineering at Northwestern University, expecting to complete his degree by the end of this month. He earned both his bachelor's and master's degree from Seoul National University. His expertise lies in artificial intelligence and computational mechanics with a research focus on advancing predictive scientific AI by integrating principles from computational mechanics and applied mathematics. He specializes in high-performance computing on multiple GPUs to solve ultra large-scale scientific and engineering problems. With that short introduction, the floor is yours and you can start your presentation.
Is it possible that we can introduce Rob at the same time?
Because you are the speaker, I only put your biography there to.
Oh,
Yes.
okay, yeah, but Rob, then
That's
you
okay.
you may introduce yourself
Yeah,
and
okay.
later.
Well, I can introduce later when I
Yeah,
stop.
sure.
Okay,
You
that's
can do
fine.
it yourself.
Right.
Yeah.
Appreciate it. Thank you so much for inviting us in this well-known and very prestigious talk, the Crunch Seminar at Brown University. I'm Chanwook Park, a PhD, recently got PhD from mechanical engineering of Northwestern University. My advisor is Professor Wing-Kam Liu, who is a well-known professor in computational mechanics and AI-driven physics simulation field. And I really appreciate Professor Karnidakis and Professor Miguel Bessa, who actually recommended us to give a talk in this current seminar. And I would like to Saurabh introduce here. Saurabh, can you introduce yourself quickly?
Okay. Hi, good afternoon, and thank you for inviting me and Chanwook to this seminar. I'm Saurabh Shah. I'm an assistant professor in the Department of Aerospace and Ocean Engineering at Virginia Tech. I graduated in 2024 from Theoretical and Applied Mechanics Department. I worked in Chanwook's group. We worked with Professor Wing Liu. And after graduation, I joined as an assistant professor here at Virginia Tech. So my research expertise lies in scientific machine learning, multi-scale simulation, and application to advanced manufacturing and microstructure design. I'm very glad to be here and I look forward to the talk. Thank you.
Thank you, Saurabh. Okay, the title of today's talk is Interpolating Neural Network, and its derivatives for the next generation of predictive scientific AI. And I will get started. So here's a brief outline of our talk today. I will start with an introduction and motivation, and then we'll show the interpolating neural network architecture, and then it follows with numerical tests, such as INN for solving a PDE, INN tensor decomposition for training simulation data, and finally INN tensor decomposition for solving a parameterized partial differential equation. And then Saurabh will introduce the recent INN derivatives developments, such as expressible INN, Kronos, transfer learning, and others. And those are the references that mainly consist of today's talk, especially the first paper written by me and Saurabh on the interpolating neural network, which is currently under revision in Nature Communications, is the core part of today's talk. Okay, with that, I will start with the motivation. So we have seen a great success in large language models in recently. And one of the reason that actually drove us into that success is the scaling laws. And this scaling law in large language model is published by OpenAI in 2020. It simply states that there is a scaling law between the performance of a model. Okay, let me put this way. Yeah. So there's a scaling law between the performance of an AI model in LLM versus amount of compute for training, dataset size, and parameters. So it simply tells us that if they keep increasing those three things in x-axis, they will keep increase the performance of an LLM. And since this 2020, and OpenAI decided to invest a lot of their resources and money to put more effort on increasing those three x-axes, and they finally came up with the ChatGPT that made this great success. Now, we can ask this question out of this scaling law. If the goal of the entire AI community is to build or invent an AI model that works like a human brain, which we call AGI, right? Artificial General Intelligence, can we simply follow this scaling law? Meaning that can we simply increase the compute amount, dataset size, or parameters to achieve this AGI, the overall goal of our entire AI field? Our answer currently is no, because even the human brain is divided into multiple parts, and each part is expected to work differently. So if we draw an analogy and project the current AI models into this brain figure, for example, the brain is divided into left brain and right brain. We all know about this. So left brain does the analysis, logistic things in our brain, in our intelligence, whereas the right brain is doing the creative and intuitive parts of our brain. So if we project the current AI models in this field, although it's not a strict distinction, but we can project the predictive AI on the left brain side and the generative AI on the right brain side. And for each AI model, we are expecting actually different things. Or for example, we don't want like scientific AI perform similar to like music AIs, right? So in order to achieve the AGI, our speculation is that we want to have different AI models that performs really well on specific tasks. So among those different AI models, we want to focus on the scientific AI under the predictive AI, which is the target of this talk. So now we want to define what is the predictive and scientific AI. So we want to specify our problem statement like this. So given input variables, where the input variable is classified into three things: spatial variable xs, parametric variable xp, and temporal variable xt, and the output is u as a physical quantities. So the goal is to find out the relationship between these two. However, this is not a simple data-driven problem because there is a governing law, governing scientific principle, which is called partial differential equations. So in order to solve these problems, regarding solving these problems, I want to bring two quotes from the famous entities in our field. One is Stefan Wolfram, who is the founder of the Mathematica. So the great opportunity to move the science forward is to combine the strengths of AI and of the former computation paradigm. In another quote from DeepMind, the AI will enrich the traditional approaches to modeling complex systems rather than replace them. So the key idea is that we want to integrate the core principles of computational science, numerical methods into the AI to advance the field in predictive scientific artificial intelligence. So we can categorize the tasks in predictive scientific AI into 3 parts. And we assume that given that there is a governing parameters PDE, so this is a PDE parameterized with XP parameters. The goal is to find a surrogate model, U of XS spatial, parametric, and temporal variables. The one approach can be the data-driven approach. So we'll first sample out the parameters XP and run simulations using standard simulators like finite element or finite volume. So we solve this first and stack the data as I call this as training data. And then the next task is the training or learning based on the data. This is a data-driven approach. Or we can even go straightly from the governing PDE to the surrogate model. This is a data-free approach, and we can think of the parameterized PIN, physics informed neural network, as one of the examples. And once we achieve this surrogate model, then as an engineer, what we want to do is calibration or in solving inverse problems. However, in predictive scientific AI, we have several challenges that we want, and among them, we want to mention 3 challenges in this talk. One is the generalization capabilities. So in general, AI models are less accurate than numerical methods, especially if they are the problem statement is well established. So for example, the FNO, in FNO, we typically deal with the error level of 10 to the negative 2. However, in FEM or other FEM derivatives, we are dealing with really high accuracy, 10 to the negative 8. And the other thing is that we can have a well-known convergence for FEM or numerical methods. However, in AI-driven methods, it is very hard to derive the convergence in general. The second challenge is scalability. For both data-driven AI models and also the standard numerical methods, they struggle a lot for high resolution. I mean, extremely high resolution problems or high dimensional problems. And this brings us to the next challenge, which is sustainability. So in order to tackle those highly challenging problems, people are making bigger and bigger neural network.
And so this fundamentally says our challenge is to figure out how over the next decade we think about compute efficiency as the #1 priority.
So as Dr. Lisa Su mentioned, the goal is to find out an AI model that is sustainable, scalable, and really accurate. So our goal is to develop such a model, and we want to measure the 5 performance metrics. We want to find out a model that can outperform in those 5. One is grid resolution, so how much resolution that we can achieve. Model accuracy is the next thing, and computation speed as well. And uses RAM and disk storage. So we want to use smaller amount of those 2. All right, so this was the motivation or introduction slides of our talk. Then we want to move on to the INN. What is interpolating neural network? The simplest example of an INN can be the linear interpolation. So this is a very simple problem. We want to approximate this very simple 1D input, 1D output sine function, sine 2 pi x, with 6 grid points, or j grid points. So in this example, we discretize the domain into 6 points, and we come up with linear interpolation function on each grid node, like this. And we measure the function value at each grid point, u1 through u6, and we use the interpolation. So this is how linear interpolation or linear FEM does to approximate such problem. And the core thing here is how we build those interpolation functions. And if you look into one of the functions, let's say we are looking into the function and at node or grid 3, this function is made of three things, three coordinates actually, x2, x3, and x4. This is a functional form, right? On the left side, at this element or segment, we use x2 and x3 to build this linear function. On the right side, we are using x3 and x4 to get this linear function. Then our question is, can we come up with better approximation, better interpolation function, which are nonlinear, in the same architecture? And the answer is yes, by incorporating more nodes, more neighboring nodes at this, from the center node. So in this case, we are considering, for example, 2 nodes from the left and 2 nodes from the right. We call this patch size. So in this case, the patch size is 2. So we're still looking at the interpolation function at node 3, but we have larger patch size, S2. Therefore, we have more coordinates, node coordinates to be considered from x1 to x5. And also there are basis functions that constructs this nonlinear interpolation. So we can choose specific nonlinear interpolation functions. You can view this as an activation function in like in MLP, and the total number of those basis functions, P. So due to the time limit, I didn't go through the details of the derivation of those interpolation functions, but all the details will be provided in each paper in the reference list. So with that, I want to go back to the previous example, but now I want to change this to a training example. So given this ground truth function, which we sample out 10,000 points randomly, and we just train the data. So we first started with linear interpolation with only 6 grid points, and this is what we got. The result is not bad, but this is not optimistic, right? So how we can improve this prediction accuracy or approximate accuracy? What we can do is use the nonlinear interpolation. We use the patch size 2, and with the polynomial basis functions, meaning that we are using x and x squared, and also there's a partition, since for the partition immunity, we have 1. So by using this nonlinear interpolation function, we are getting much better approximation accuracy, right? But we are not even not satisfied with this result. So we changed the basis function from polynomial to sine, especially the second basis function exactly matches with the original ground truth function. In this case, due to the reproducing property of the interpolation functions, we are able to approximate the original function exactly without changing the number of trainable parameters. The trainable parameters are still these 6 points, 1, 2, 3, 4, 5, 6. But we can achieve very low accuracy. This is actually pretty close to the machine error of the Python. And this is the strength of INN. So we can adapt the activation function and the patch size, all these hyperparameters to come up with a better approximation with function. With that, I want to move on to test problems. I want to show 3 things. The first thing is a solving. This is a standard FEA type of solving problems given the fixed parameter set. So for general problems in 3D input domain, what INN does in terms of constructing the functional space is that we first divide the domain into elements or segments. In this case, I named this as J grid points. And for each grid point, we construct INN interpolation functions. The ingredients are still the same, right? We have patch size as neighboring coordinates, nonlinear basis functions, and number of basis functions. Now, at this point, I would like to mention our previous development history. So we actually started this approach from the original HIDDEN paper. HIDDEN stands for the Hierarchical Deep Learning Neural Network. So with HIDDEN network, we are able to replicate all existing FEM FEM models in terms of neural network. And then we moved on to the convolution hidden that leveraged the convolutional layer to approximate these nonlinear functions, nonlinear interpolation functions. So the figure that described in here is exactly the same as the convolution hidden network architecture. So after we construct this nonlinear function on each grid point, then the output is the readout operation. We multiply with the nonlinear function with the grid values, the nodal values, and this is the output of our functional space. So let me briefly compare the INN with high order finite elements because we are talking about nonlinear and highly smooth interpolation functions. So there's not that much difference if we only look into the order polynomial 1 approximation. So in linear FEM, we have 729 grid points in this case, where we have 9 by 9 by 9 grids. INN does a similar thing, where we have the center element and the neighboring elements are the support domains. The difference takes place for higher order finite element. So in higher order FEM, what we do is we add nodes on each element. That's why we have so many nodes in each element. Please understand that I tried to draw dots here on the top side and right side. It was too messy, so I just removed it. But imagine that there are a lot of dots here. So total, they have 35 or 30, nearly 36K grid points for P equals 4 higher order approximation FEM. However, in INN, we keep the same mesh. We are still relying on linear mesh. However, we are increasing the connectivity between the nodes to construct those nonlinear basis functions or nonlinear interpolation functions. So finally, if you look into the assembled system of equations, the global stiffness matrix looks like this. So for high order FEM, the size of the matrix is pretty large, but the bandwidth is pretty narrow. However, on the nonlinear INN, we are having much smaller system of equations, but we have larger connectivity between the nodes or degrees of freedom. So that is the difference, key differences. So as an example, I want to introduce this problem where we originally got this from ANSYS from our collaboration. This is a stress concentration problem on this rocket geometry where the bottom is fixed and the inner cylinder is undergoing through a traction boundary condition. And the stress concentration happens at this connecting part. So in this slide, we compare INNs with ANSYS linear tetrahedral element, ANSYS quadratic tetrahedral element, and the reference solution. So reference solution is obtained by running ANSYS with 20 million degrees of freedom quadratic tetrahedral elements. So what we observed is that to achieve the level of to achieve the convergence level of the maximum, the von Mises stress, INNs were able to get this 12 times less degrees of freedom than ANSYS, meaning that our model is 12 times memory efficient or computationally resource efficient. So this is basically due to the fact that our system of equations can be constructed much in a smaller way, although we have larger bandwidths. Okay. Now I want to move on to the next problem, which is from the simulation data, how we can come up with a surrogate model. In this case, I want to introduce the idea of tensor decomposition, especially the canonical polyadic tensor decomposition. So I think most of us know about this CP decomposition, but I will briefly explain what it is. So CP tensor decomposition decomposes a matrix or high order tensor into an outer product of vectors. For example, this U matrix has J1 and J2 components in its dimension. Now we want to approximate this matrix into an outer product of vectors A and B, but solely with A and B is not enough. The accuracy is not enough. So we are keep adding more sets of A and B. We call this mode. So total m different sets of A and B vectors will be needed to approximate this original matrix. So for m, we call this as a mode. So I will introduce the architecture of an INN with tensor decomposition for this training problem. Although for this 1D simple problem, we don't even need the tensor decomposition, but I will revisit the same problem and show you this as our network architecture. So since this is only one input and one output problem, we have one input on the left and one output on the right. In the middle, we only have one hidden layer with one hidden neuron. And what we do is from input to the hidden neuron, this is connected with a weight, or we can call this as a learnable activation function, similar to KAN. So if you're familiar with the concept of KAN, this is exactly the same as KAN, except that we use interpolation functions. Whereas in KAN, they're using cubic splines. So that is one of the critical differences between KAN and INN. But however, in the 1D problem setup, they are pretty much the same. So let me explain again. So this learnable activation function can be viewed as a parameterized with 6 points. Now we have U1 through U6. So we only want to figure out the coordinates, the values of U1 through U6, and find out the best set of these that minimize the loss function. So this was a problem statement for the training problem of this 1D case. Now we want to move on to high dimensional cases. So for high dimensional problems, especially for training, we want to leverage the tensor decomposition idea. So basically, we have 1D interpolation for each input, and we do the product, and then we do the summation over the modes. So it's a product and summation. Compared to CAN that uses two double summations, summation and summation. But the key difference is that we are leveraging this product sign here from the tensor decomposition. So procedure is like this. For each input, we construct INN 1D interpolation for each input. That's where we define this learnable activation function. And then on each node, we do the multiplication. This is a key difference between KN. We do the multiplication because we are from CP tensor decomposition. And finally, we do the addition at the output layer. That's it. And we only need one hidden layer. We are not needing multiple layers to approximate a function. Whereas KANs and MLPs, they typically use multiple hidden layers. And that is the reason why our INN network with tensor decomposition, the trainer parameters of INN only scales linearly with each component. So number of modes or neurons in this case, we are scaling linearly with each of them. So how this is different from MLP? So let me briefly go over this architecture of MLP. But I think we all know that the number of the total trainable parameters scales quadratically with the number of neurons, which is M. And H is the number of hidden layers. And also, we assume that the number of neurons, M, is the same across the different hidden layers. That's for simplicity. So for summary, if we compare MLP and INN in terms of network architecture, MLPs are using deeper network, but even the KAN uses a deeper network, but INN with tensor decomposition only needs shallow architecture. Single layer is enough. That's why the number of parameters scales linearly with all different variables. Okay, for demonstration problem, actually it's from this paper written by Jia Chen. We solve this parametric heat conduction equation where there are two spatial input, x, y, and x and y, and K is the material property, and P is the heat source that goes into the sourcing function. So P goes into here, and B is the sourcing function, and the time is the temporal variable. So what we did is that we sampled this many parameters in the parametric domain, and we solved finite element in each set of parameters, and then gathered data. So in total, there are over 5 million data points. And given this data, we train this model. And now we compare MLP with INN tensor decomposition. We choose different hyperparameters, but the trend was in general the same. What we could observe is that INNs with tensor decomposition converges much faster into a lower error with less trainable parameters. So the trainable parameters, the INN was smaller, time was faster, error was much better, and the inference time was comparable. So this summarizes the benchmark problem in INN-TD training. Now we move on to the data-free approach. The data-free approach, as I explained, we want to move directly from the governing parameterized PDE to the surrogate model. So as a benchmark problem, we came up with a problem statement with 8-dimensional inputs. In this case, we are solving parameterized heat transfer problem in additive manufacturing, where we have X, Y, Z spatial coordinates as an input and time as an input as well. And we have K as a material parameter, and P, eta, B, those are the laser parameters that goes into the forcing function. So basically this K is in the material property, but P, eta, D, those are in the forcing function. And the reason why we want to solve this type of parameters problem is for control in additive manufacturing. So in additive manufacturing, Saurabh, if you want to add comments, please go ahead. In additive manufacturing, what we want to do is we want to change those laser parameters to achieve homogeneous temperature distributions as it prints out. So that's the reason why we want to solve this type of parameterized PDE in AEM simulation. Okay, and the output is the temperature. So we compare two different methods. One is the data-driven with finite difference methods. So basically, we create the data using finite difference, and we stack the data and train it. And the INN-TD is the data-free approach. So in data-driven approach, what we have to do is we sample out the number of parameters, the different parameter sets, right? Since we have 4 parameters, we assume that we should sample out 10 parameters for each. So total number of simulation required is 10 to the 4 power, so 10,000. And with FDM, we are able to run only a resolution up to 25 micrometer. And of course, these are the estimated numbers because we weren't able to run 10,000 simulation with the same with this expensive simulation. But with the estimated numbers, the total time of data-driven problem approach took 100 days, and this many storage, and this, and if we convert this to computing cost, it corresponds to around $5,000. However, with INN-TD, the number of simulation required is only 1 because we are solving all at once. It's like similar to parameterized physics-informed neural network. The idea is, yeah, this is a data-free. And we are able to achieve final resolution, much better speed up, much better storage save, and computation cost saving. We also verified the accuracy of this our model with the final element simulation. So we specified parameters. So we fixed those parameters, and we did the inference on the obtained surrogate model of INN-TD, and compare this result with finite element with the same parameters. So this is just a single run, and we measure the accuracy, and it really matches well. The R square value was around 0.9964. This is written in this paper. All right, with that, I want to introduce Saurabh, and he will talk about the recent developments on INN derivatives.
Thank you so much, Chanwook. Yeah, I'll go over very briefly on the other derivatives of INN that we have been working on. Yeah, Chanwook, please go ahead. So the first thing that we wanted to do is that we wanted to play around with the interpolation function and the architecture of INN itself. So the idea was that how to make these interpolation functions more interpretable, and also how to come up with an architecture that is more closer to the, I would say, the traditional architecture. So from there, we came up with this kernelized version of the INN, which I'm calling Chronos. The main features are that of these structures, structure are that we are using a kernel expansion hierarchically and recursively. We have compositional layer just like a neural network could have, and all other architecture are quite similar to INN. For example, if you have this functional space of n number of input parameters, what we want to do, we want to come up with these projected one-dimensional subspaces. Chanwook, if we can go ahead. And in all those one-dimensional subspaces, what we want to do is that we want to create a multi-layer approximation using kernel for each mode, and then combine the mode using tensor product, just like a traditional INN2. With this architecture, we tried out different benchmark problems, just like what we did with INN. So I'm not going to present all of them. Here is one function that is, we call it Sobel G function, and we introduce some noise. It's a 20-dimensional function. And we want to see that with this noisy data set, how well this kind of kernelized version of INN perform. And you can see this is the comparison between comparison of this kernel-based function of Kronos, kernel-based approximation of Kronos, and random forest, XGBoost, and MLP. And it's obvious that this method uses orders of magnitude smaller number of training parameters. It's almost at the same level of training time, and inference time is very fast. And you can see the accuracy is much better than all other contemporary methods that you can see. Now, moving forward, we tried, with the standard PDE solution, since it's completely supported, all the kernels, and we use this Poisson's equation. And the whole method structure actually is quite similar to what INN do, but with the additional flexibility that you could actually add multiple layers right now to get more nonlinear approximation. So if you go to the next slide, I think that there the comparison is much better, and you can see that when compared to a linear or quadratic finite element, these kernel-based methods are orders of magnitude more accurate for the same number of degrees of freedom to be solved, and the convergence is quite similar that we expect for quadratic finite element with which much smaller number of degrees of freedom. And we also tried compared with it CANs as well, and it showed much better performance than CANs. So the more interesting part is how to do the inverse solution with this scheme. Now, since this architecture is completely separable, we can think of many interesting ways to do inversion. One of the ways could be using algorithms like fixed point iteration or Gauss-Newton method. So we tried one of that. So you see, this is a two-dimensional function where the output u is a function of inputs x and y. And once we train the parameters in forward way with sampling from x and y data to approximate u, and if you want to come up with the x and y sets for a specific value of u, say for example 0.5, how would you do that? And this is the example application that we're showing here. On the left, you can see the exact solution for u equals to 0.5, all the sets of x and y that would give that value, and the right one is the model that is trying to give us that value. Another good thing about this algorithm is that since it's fixed point iteration, you can start with all different initial points, many different initial points, and you can easily parallelize it among many GPUs and CPUs, and that's what we did. So by here, the DUF would actually means that how many initial points we are actually starting off with. And you can see that this inverse solution, when parallelized, is very, very fast, within orders of millisecond. And we get RMSE value of around 10 to the minus 3. So this opens up a very big opportunity, especially when we need a rapid control system, for example, as we would need in a 3D printing system, as Chanwook has showed. And especially in my lab, I'm trying to explore how to implement this software in a real 3D printing machine to do real-time control and monitoring of the process. Another important and I would say interesting application of this method is how to come up with a closed form functional form of different scenarios. So that's what we are calling the expressible interpolating neural network. So usually what we would do classically is that we would have some observation of a physical phenomenon, then we would produce some hypothesis, and then we would come up with some kind of expressible formula. So that used to be the case for a long time, but nowadays what we do is that we have this data or observation, we call it. Chanwook, if you can go ahead and yeah, directly from the observation, using some kind of regression or machine learning method, we want to come up with this expressible formula. So again, because this method is separable and it can give us one-dimensional approximation space of each input variable, we thought, why not we try this out and come up with and try to see if we can come up with some expressible formulation for any physical processes. And that's what this work is all about. Now the crux of the method is that the positive thing about this method is that yes, it is separable and it can have separable expression, but on the other side, not all the functions that are out there or not all the phenomena that are out there are actually completely separable. So that's why we have added a separability check. What it does, it samples whatever function that we want to approximate and tries to come up with the Hessian of the function. And based on that, it tries to decide whether it would use a one-dimensional approximation of all the parameters and then use some symbolic regression to come up with the formulation, or it uses the entire approximation, not separable one-dimensional approximation, and then use the symbolic regression part. So we have used that checker in between, and then used this INN as the intermediate surrogate, and then added the symbolic regression part so that it can actually come up with some kind of expression. So this Hessian-based separability score is pretty simple actually. So if you have an additive expression, you compute the Hessian of all the functions, and if it's a multiplicative expression, you do the logarithm and then make it additively separable and then calculate this Hessian matrix. And you just notice that whether the matrix is diagonally dominant or not. If it's a diagonally dominant matrix, then you have a very clear idea that it is multiplicatively separable. But if the other off-diagonal terms are also important, then you have some idea that it may not be a good idea to use the separable approximation and then do the symbolic regression. So we tried this method with different benchmarks. So these benchmarks are here in the slides, but not right now on the slide that you are seeing. But there are different, like 8 or 9 multi-parameter functions that are out there that we tried out with this and compared to this method with. If you go ahead, Chanwook.
Oh, sorry.
Okay. Yeah, so this table, so this V1 to V8 are all these different functions, and you can see that we have compared with PySR, which is just a direct symbolic regression with genetic algorithm, and symbolic CAN. So we choose CAN because this is, I would say, the closest architecture that we are trying to do with INN. And as a baseline, we used the same number of training parameters as an INN to choose the model for CAN. So all the performance are with the same, almost roughly similar number of trainable parameters as INN. And you can see the black bold numbers that say 0 or some other numbers. Those are the cases where it has the best performance. And one of the functions you can see on V4, actually PySR, which is the traditional genetic algorithm, is doing slightly better than Xene. And this is one of the cases where the function itself is not very separable, and we cannot beat like general symbolic regression in terms of accuracy, but of course you can see in terms of time we are taking roughly about 1/3 of the time compared to PySR. The next slide. So we tried to solve some real come up with some expressions from real experimental data sets. One of the data sets that we used is coming up with the hardness of materials based on some material parameters such as bulk modulus, shear modulus, Poisson's ratio, atomic radius, and so on. And with our method, we could get this expression. And in the literature, the best, I would say, approximation on this data set was from an algorithm called CISO, and it got around like 2% of relative error. But with our method, we got like around 4.49%. And we also tried out on different data sets on fatigue life prediction of metal alloys, coming up with the yield surface of a material from data. And in all of those cases, the algorithm did very good job, and we'll incorporate all of them in the upcoming publication that we're working on. So I'll not go over, for sake of time, too much on the reinforcement learning and transfer learning parts, but we also made some significant strides over there as well. And it turns out that because of the separability part, transfer learning works much better when the feature spaces are not completely matching. For example, your source data set has maybe 10 features, but your target data set has 20 features, then you don't have to resort to a latent space to transfer your parameter, just like you do in other traditional MLP cases. And we are also seeing some promising results for reinforcement learning, but we're trying to report them as soon as possible. So with that, I'll hand over to Chanwook to finish up our talk and summarize. Thank you.
Right, thank you, Saurabh. So since we are in the early stage of INN developments, we have tons of items to explore. Those are the list of ongoing research and potentially the collaboration topics, especially with the audience of today. We are open to collaboration on those specific topics. If you can suggest more, we are welcome to learn and discuss. So the first topic is images. So INN have been applied for image classifications, like classifying fashion MNIST dataset or ImageNet dataset. Also, the replacement of MLPs in standard and well-known image models like CNN or Vision Transformer is currently being actively researched. And for problems with statistical variations, like probabilistic problems, in Professor of Income News Group, we are actively working on Bayesian neural network, where the nodal value U now is represented as a probabilistic distribution. And on the operator learning side, we leveraged the TD's remarkable scalability, and we were able to reinvent the operator learning through interpolating neural network. So this is actively being researched. Especially this is being researched for additive manufacturing problems, where we want to do the model-based control of the laser power for laser parameters. The next thing is problems with extremely high nonlinearities. So for such problems, the tensor decomposition is not pretty well in terms of the separation of variables. So our group, one of our previous postdocs, Dr. Ye Lu from UMBC, he is actively working on the extended tensor decomposition, where we introduced fully coupled terms on top of the tensor decomposition to model these highly nonlinear physical problems. Next, the reinforcement or transfer learning. So INN derivatives are actively being developed for this purpose, R and TL. Finally, the multi-scale solvers, especially the consistent clustering analysis. Actually, this was originally developed by Professor Miguel Bessa in Brown University, and he's the original developers when he was in our group. So we are currently considering of integrating these SCA capabilities with the INN solvers. And this is an ongoing joint research between Northwestern and Virginia Tech. So with that, I would like to conclude our talk, and I really appreciate your time and your attendance, and we're open to questions. Thank you so much.
Thank you so much for your great talk. Do we have any question for the speakers from the audience?
Before we go to the Q&A, I forgot to mention the training examples that you have shown so far is provided in this GitHub repository. So please go ahead and see what's there.
Yeah, thank you. Any comments?
Maybe I have a question. Hi, Chanwook and Saurabh. It was a really nice talk. Thank you so much for sharing your work with us. My name is Juan. I'm a PhD here at Current Group. Maybe one question, did you compare, because there's a little bit of similarity, for example, with tensor neural networks and in the case with separable things, where they also do this kind of like a tensor decomposition. And for example, in the case of separable things, what they observe was like, when the solution is separable, things work nicely and everything's good. But when the solution is not separable, things started, I mean, they were still good as long as the feature size is big enough, but then you were limited up to some point, right? Do you explore a little bit around this area?
Yes, Shanta. Thanks for a great question. Yes, we don't want to claim that INNs is the best for all different problems. So there are specific problems where INN can fly, or there are other problems where INN cannot fly, or MLPs others fly. Yes, in general, functions that are separable is really well with INN. Let me go back to one of the examples here. Especially like this problem. This is a parabolic PDE, right? Where we have pretty good convergence behavior. And this is not a chaotic problem. This is a purely diffusion-based problem. So in this case, we are really performing well. And there is another reason that why we are outperforming MLPs a lot. So MLPs are made of global function approximation, right? So the entire function space is approximated as a global function. However, in INN or interpolation, those interpolation-based methods is using compact supported basis functions. So our approximation fields are constructed as local basis, meaning that for such problem where we have local behavior, right? It captures really well on modeling those local behavior or problems that has high frequency modes. However, for problems with less fluctuation or a low frequency, the performance of MLPs and INN sometimes are comparable, or even MLPs can outperform INN in such cases. So Rob, do you want to add some more?
Yeah, I think everyone, this is a fantastic question, and there are two things. One is that are you asking that if the function that you're trying to approximate that is itself non-separable, or the PDE that we are trying to solve that has non-separable terms? Because there will be two approaches to deal with those two things. That's why I'm asking.
In the end, you will be trying to approximate a function. It could be either the solution of the PDE or the solution itself, right? So
yeah.
I think that
so for example, see, this is one example of MPDE. So even if the source term, say for example, if it's non-separable, just like you would face in additive manufacturing, in any case of additive manufacturing or some other robotic application, perhaps. So there is one like a trick that we use right now to make the source term separable. So I talked about the expressible part of the INN, right? So you can use that to come up with actually a separable expression, and then use your analytical formulation to come up with the weak form. So that's when like you are faced with, okay, my PDE itself does have some term that is not separable itself per se. And on the other end, like if the function is itself non-separable, then this is actually, your question is kind of the motivation of like checking that whether it's actually separable or not at all. So that's why we want to make that check. But if the separability score is very low, then it's just, yeah, sure, this method will not be as good as the cases where the separability score is very high.
yeah. Oh, okay. Yeah. Great. Thank you both for the answer. Well, a little bit more if you try to compare a little bit with tensor neural networks or with separable beings.
Definitely. We'll do that. Thank you so much.
Yeah, because it's a bit more similar. Because in CANs, actually, when you were saying that you have like the double summation for CANs, that is true. But the thing is that that's what you're allowed to do it, right? In CANs, you cannot add multiple, you cannot add products, because then you're out of the card. You're out of the Kolmogorov-Arnold representation theorem. So I think that if I would say if there's more similarity, would be more similarity with tensor neural networks than with CANs. And in the case of CANs, there's also a thing that is called separable CANs, where they do somehow along the same lines that they will use the separable structure, and then instead of using a normal MLP, they will use a CAN.
Yeah. They call it multi-CAN or something like that, right?
I think they call separable CAN. And this is by the Pacific Northwest National Lab, if I'm not wrong. They are the authors of that part. And the reason why I'm pointing that out is because one of the tables which shows something really interesting is that when you say that you get like you go from 1,000 hours, 100 days to 1 day, and it's something quite interesting. And for example, this is what something that they were also claiming in the separable pings paper. They will have like times 100 speed up, but it was because they were like feeding 1 million points for training in the MLP, and the other case they were only using like the 1,000 and 1,000 for each one of the dimensions. So that's what I said. Maybe comparing with tensor neural networks here, it will be like a better benchmark. Like
Thank you.
because
Yeah. Thank you so much. We'll definitely try to do that.
Yeah, we
okay.
actually did a benchmark on the tensor neural network in this paper. INNTD. This was accepted in ICML recently, so you'll be able to find this source in this case. But we try to do the benchmark and do the same problem using the CP and MLP. So the MLP constructed with CP decomposition. So in that case, our INN was better than that model as well. So thanks for
Okay.
However, for this problem, we haven't tried that
Yeah,
CP.
for PDs,
Okay.
we did not try yet.
Right.
But it was a really nice talk, and your approach is really interesting. Yeah, congratulations both.
Thank you so much.
Thank you so much.
And I would like to highlight one of the key differences here. Even with the CP and MLP or the tensor neural networks, the way they solve this problem is they use a collocation method and optimization-based solvers, right? However, in INN and tensor decomposition, we are based on Galerkin methods. So basically, we are solving almost the same as the way that we solve infinite element. So that brings us the efficiency of the solver. And that was the reason why, even with these 8-dimensional problems, we were able to solve this in 15 minutes using only one GPU. Right. Thanks for the question.
Thank you so much. And I do agree with Juan. It's very innovative and great work.
Thank you.
Do we have any other questions, comments from the audience?
Yeah, actually, I would have a question. So just turning on the camera. Hi, I'm Sasha Ansel from Brown University. I've been thinking, there's an idea floating around out there in the computer science uh, department that some people call sum product networks or einsum networks or probabilistic circuits. It's a very similar idea that you have for this a sum of tensor products, and you create your model like that. With maybe one difference that I'm recognizing here is that you impose additional constraints on the graph of this sum of
So you mean the
tensor.
chronicle delta, right? So we can exactly pass the specific point, like the Dirichlet boundary condition.
I'm more referring to that when you impose certain constraints on the graph of your tensor product network,
Yes.
then you can retain properties like tractability at inference time, right? So you can actually almost analytically compute statistically moments if you can impose those constraints on the structure by allowing you to exchange sums and integrals and a distribution of multiplication with the integrals. So that's where there's a kind of, maybe it's a cottage industry in computer science that they call sum product networks, or more modern term probabilistic circuits. And so maybe this is a bit of a difference here, that you're not constraining yourself, right, regarding this. So you don't necessitate yourself to have a tractability at inference time. So, but what I found in my own experience in these probabilistic circuits, those beasts can be really difficult to train, and are quite unstable, or at least very sensitive to initialization. Now, what you showed, well, doesn't show there the similar kind of behavior in terms of sensitivity or instability. And it may be attributed to the additional structure that you'd want to impose for tractability at inference time. I don't know, actually. Could be the reason. So then my question is, in this interpolating neural network, what is the limitation actually? Do you observe that consistently the training is not too sensitive to initialization? You don't need to be so careful like in probabilistic circuits, or
You raise a really good point. I would like to share one figure with you, but Saurabh, do you have any other comments to respond?
No, Sasha, thank you so much. That's great question, and we face those problems. It's not that we did not face those problems, especially when so it's actually a long history. So we started working on it around, I think, 2020. So initially we faced those problems. So we started off as like try to solve the PDEs, use as a PDE solvers. So that's why those shape functions came into place. But then when we try to scale up and try to be more, I would say, aligned with neural architecture and added, say, for example, as I showed in my kernel stuff, adding more layers and more recursive functions, just like a continuous neural network would behave, then we saw that if you like, then we saw those kind of unstable structures. For example, the training would blow up, and depending on how you're segmenting your parameter space, the network would not converge. So for that, yeah, Chanuk, Chanuk already has the table. I can come back to my discussion. I'll let Chanuk finish his thought, and then I'll come back to that, what I'm trying to say. Yeah, Chanuk, please.
All right. Thank you, Saurabh. So yeah, in this paper, IN and TD paper, this is the whole table that we presented in the paper, where we also compare the initialization aspect. So we changed the initial seed parameter for the initial guess, and this is standard deviation is telling us the train and the training and test accuracy at the conversion point. And as you can see here, INNs are having much lower standard deviation than the other models, meaning that we are very good at converging at some value and much faster than existing models with less fluctuation.
Yeah, and coming back to my point, it seems like if I use one layer, like do not use recursively multiple layers, and then add kernel or interpolation or shape function, whatever, it's very stable. Once you incorporate more and more layers, depending on the problem, there are some cases that actually it's trying to blow up, but we are still figuring out exactly how to solve that issue. Especially when you go to like 4 or 5 layers, and do you even need that? That's another good question.
It depends on your problem, right?
Right.
I know what you could look at, what helped in my case was a batch normalization. So when you have, I'm not sure if this will hold for your unconstrained case, but if you have the constraints on the structure, where you have decomposability and smoothness, and then you do the batch norm, you can absorb it into the constants, and basically everything remains intact. That might not be, not sure if this will hold here in this unconstrained case. Yeah, batch norm, maybe. But I'm still so what you're saying is that the instability only arises as you increase the depth. May I ask, what I didn't quite understand is how many basis functions you used on the input layer side, typically.
Yes, that's one of the also the reviewers asked to us when we were doing the review. Typically, we start with like 20 to 40 grid resolution on each input dimension. So meaning that we have, let's say we have 40 grids in each dimension, then we have 40 interpolation functions, right? Because we have 40 grids. Or since we are adding different modes, keep adding those modes, we can even change our interpolation or discretization across different modes. So for example, if we can start with relatively coarse resolution, let's say 5 grid points in each direction, so 5, 5, 5, and so forth. So we are having only 5 basis functions to represent, but on the additional modes, we can keep refining it. So basically, we can also capture both the low frequency information and the high frequency response at the same time. So this can be viewed as a multi-resolution aspect approximations.
So long story short, so basically how you're discretizing. So each discretization segment will have one basis function attached to it.
Yeah. Okay. No, I understand that. Yeah, very interesting idea. If you happen to go into constraining the graph for tractability of statistical moments, and if you happen to observe instabilities or absence of instabilities, I'd be very happy to receive an email from you. Thank you.
Sure. Yeah, we'll email you. Thank you.
Thank you so much. Do we have any other questions? Any comments? Okay, it's time to close the session. Thank you so much for joining us today and for taking your time to present your great work. I hope everybody has a great weekend ahead. Bye.
Thank you. Thank you so much for inviting us.
Appreciate it.
Have a nice weekend.
Bye-bye.